What if humanity is not the first intelligent species to walk the Earth? It sounds like the opening line of a science fiction novel, yet this is a question that serious scientists have started to explore. Beneath our feet, buried in layers of rock that stretch back tens of millions of years, lie chemical clues that don't always match natural explanations. These clues hint at something unsettling, that intelligence, industry, and civilization may not be unique to humans, and that the Earth itself could have hosted other advanced species long before us. To most people, the history of our planet is divided into neat categories: prehistoric life, dinosaurs, the rise of mammals, and finally humans. But the deeper you look into geological time, the more you realize how small our chapter really is. Earth has been evolving for 4.5 billion years. In that unimaginable span, our industrial civilization has existed for only a few hundred years. Even if you include early agriculture and written history, human presence barely registers on the planetary timeline. Compress Earth's history into a single 24-hour day, and humans arrive in the last second before midnight. Our factories, our skyscrapers, our satellites, all of them occupy less than a blink in that scale. So, if another civilization had risen millions of years earlier, what traces would it leave behind? And more importantly, would we even notice? The first unsettling truth is that physical structures do not last. The monuments we think of as eternal, the pyramids, the Great Wall, Mount Rushmore, are fragile against the relentless forces of nature. Wind, rain, ice, earthquakes, and chemical erosion eat away at stone and metal with patient persistence. Within 1 million years, even our most enduring landmarks will be reduced to unrecognizable rubble. Skyscrapers collapse in decades if left untended. Bridges rust away in centuries. Entire cities crumble in just a few thousand years. Chernobyl, abandoned only a few decades ago, already shows how quickly nature reclaims the works of humanity. Forests spread, roots crack concrete, animals move into decaying buildings, and rust devours steel. In geological time, even our most advanced constructions are like footprints on a beach, clear one moment, gone the next. That means if there were civilizations before us, we should not expect to find their monuments or machines. They would have been erased long ago, leaving almost nothing visible to the naked eye. But civilizations leave behind more than structures. They alter the chemistry of their environment, and those changes can persist far longer than physical ruins. Our civilization has already stumped the planet with a unique chemical fingerprint. We produce plastics that break down into molecules unknown in nature, heavy metals smelted into forms that leave isotopic trails, and radioactive isotopes from nuclear activity that will outlast humanity itself. Even after our cities vanish, these chemical markers will remain embedded in rock layers and sediments. Millions of years from now, a future species digging into Earth's crust might find an odd layer where carbon ratios shift dramatically, where plastics leave ghostly chemical residues, and where strange isotopic patterns appear that can only come from industry. They would know that an intelligent civilization once thrived here, even if all our structures and artifacts had long disappeared. This is the essence of the Silurian hypothesis, the idea that if intelligence rose before, the only proof we would ever find lies not in ruined cities, but in the rocks themselves. And here is where the story turns even more mysterious. Scientists have already found anomalies in Earth's past that raise eyebrows. Layers of rock show sudden spikes in carbon isotopes, rapid changes in ocean chemistry, unexplained extinctions, and depletion patterns in rare elements that resemble industrial activity. None of this proves that another civilization existed, but it forces us to confront the possibility that we might not be the first. After all, if intelligence is an outcome of evolution, why should it have happened only once? The fossil record shows that brains have grown larger and more complex in multiple lineages, from dinosaurs to primates. Perhaps another species reached the threshold of technology, built cities, altered the climate, and then vanished without a trace. If so, what destroyed them? Did they consume resources too quickly? Did they destabilize their environment? Did they make the same mistakes we are making now? The introduction of this mystery is not just about asking whether we are alone in Earth's history. It is also about asking whether our story is unique, or whether it is part of a repeating cycle written into the fabric of planetary evolution. The evidence is buried deep, but the implications reach forward into our own uncertain future. Civilizations are fragile, even though we like to imagine ours as permanent and immovable. Look around at the skyscrapers, the massive dams, the endless highways, and it's easy to believe these things will stand forever as monuments to our time. Yet in reality, everything we build is on borrowed time. Nature is patient, and its tools, wind, rain, ice, fire, and simple chemical decay, are relentless. The process of disappearance begins almost immediately. Concrete, which feels like one of the most solid materials we use, is in fact vulnerable to water and temperature cycles. Each winter, water seeps into tiny cracks, freezes and expands, splitting the structure apart molecule by molecule. Each summer, heat bakes and stresses those same cracks. Steel, no matter how carefully treated, succumbs to rust, turning into iron oxide that flakes away with the next rainstorm. Asphalt highways soften, buckle, and are swallowed by grass and soil. Entire cities can crumble into ruin in only a few hundred years if left untended, and in the grand scale of geology, a few hundred years is less than a blink. We already have striking examples of this process happening in real time. In the exclusion zone around Chernobyl, just a few decades of abandonment have shown how quickly nature erases human presence. Vines crawl up the sides of apartment towers, trees sprout inside living rooms, wild animals walk down cracked avenues where cars once roared. The human-built environment dissolves back into the forest, demonstrating that it doesn't take millions of years for structures to vanish, and this is in an area where humans were recently thriving. Imagine stretching that decay process over hundreds of thousands or millions of years. Nothing would be left. Even the most durable works of ancient humanity tell the same story. The Great Wall of China is weathering into piles of stone. The Great Pyramid of Giza, which has stood for over 4,000 years, is already eroding at measurable rates. Extend those rates forward 1,000,000 years, and even the greatest human monuments become indistinguishable from natural rock. Scientists describe this as the paradox of preservation. The more advanced and high-tech our creations are, the less likely they are to survive into deep time. Stone tools, crude and simple, can last millions of years, but silicon chips, carbon fiber composites, fiber optic cables, and electronic circuits, our most sophisticated achievements, are among the most fragile. They crumble, oxidize, or dissolve in just decades or centuries. A hand axe from the Stone Age will outlast a supercomputer. This is why archaeologists often find abundant evidence of ancient hunter-gatherers, but struggle to preserve artifacts from even a few centuries ago. It also explains why, if an advanced civilization had existed millions of years before us, we should not expect to stumble across their machines or skyscrapers. Those would have been erased long ago, ground down into dust, or buried deep beneath layers of sediment. This realization raises a haunting question. If everything we build eventually vanishes, what would future scientists, millions of years from now, find when they dig into the rocks of our time? The answer is not our monuments, but our chemical trail. Civilization leaves fingerprints not through structures, but through changes to Earth's chemistry. Our emissions alter the balance of carbon isotopes in the atmosphere. Our plastics break down into molecules that sink into sediments. Our mining redistributes metals in patterns that nature does not produce. Even nuclear activity leaves behind artificial isotopes that will persist for millions of years. These traces will last far longer than any building, and they are the kind of evidence that geologists look for in the rock record. The implication is startling. If another intelligent civilization had existed long before us, it too would have disappeared physically in a short time, its cities erased and its artifacts gone. But the changes it made to Earth's chemistry could still be hidden in ancient sediments. That is the real key to detection, and it means the silence of history does not prove we are the first. It only proves that civilizations are temporary, fragile interruptions in the long geological story of Earth. The ground beneath us may already contain the whispers of worlds that rose and fell long before ours, erased by time yet faintly traceable in the chemistry of stone. The second question that scientists confront when thinking about possible civilizations before ours is what they call the detection problem. The Earth is unimaginably old, 4.5 billion years of continuous change, renewal, destruction, and rebirth. Human civilization, with its factories, cars, cities, and digital technologies, occupies only the tiniest fraction of that span. To understand how small our presence is, imagine compressing all of Earth's history into a single 24-hour day. Life itself appears around 4 in the morning. Dinosaurs roam around 10 p.m. and vanish a little after 11. Humans don't appear until the final second before midnight. Our entire industrial era, from the first steam engines to space travel and artificial intelligence, unfolds in the last blink of that final second. We are so new that our impact, no matter how enormous it feels, barely registers on the geological scale. And if this is true for us now, then the same would have been true for any civilization that might have existed millions of years before. Rocks and sediments preserve history, but they compress time in ways that make short-lived events almost invisible. A core sample of sediment taken from the bottom of the ocean might represent a span of millions of years, yet all of those years are squeezed into just a few inches of layered material. Within those layers, a civilization that lasted 10,000 years, a generous estimate for how long we may survive at our current level of technology, would be represented as a layer thinner than a sheet of paper. And most geological cores are not sampled with enough resolution to even notice something so fine. It's like trying to read a massive book by glancing only at every 100th page. Even if there was a critical paragraph hidden between the lines, you would miss it. That's what geologists mean by the detection problem. The evidence of a civilization could be there, but it might be so compressed or so thinly spread that we skip right over it. This problem becomes even more daunting when we consider erosion, plate tectonics, and the constant recycling of Earth's crust. The surface of the planet is not a permanent archive. Mountains rise and wear down, rivers cut valleys, volcanoes bury entire regions under molten rock. Most of Earth's surface is geologically young because the crust is continuously recycled into the mantle. Ocean floors, for example, are rarely older than 200 million years, a blink compared to the planet's age. That means if an industrial civilization existed 300 million years ago, almost all direct evidence of it would have been swallowed by Earth's own processes, destroyed and remade as new crust. Even on land, glaciers grind landscapes into dust, deserts bury ruins beneath shifting dunes, and forests reclaim what was once carved by human hands. The further back in time you go, the more complete this erasure becomes. So when scientists ask if we could detect another civilization, they are not imagining stumbling upon a fossilized city or a buried machine. They are asking whether the chemical scars of industry might remain in rocks that escaped recycling, or whether subtle isotopic shifts in ancient sediments might be visible to modern analysis. But even this is far from guaranteed. A civilization could rise and fall without ever leaving a clear mark, especially if it developed differently than ours. Perhaps it used energy sources that left no global chemical trace, or built with materials that blended into natural systems. Such a civilization could exist and vanish, leaving us with no way to distinguish its presence. The detection problem forces us to confront an unsettling truth. Absence of evidence is not evidence of absence. Just because we haven't found clear signs of another civilization doesn't mean one never existed. It may simply mean we don't know where or how to look, or that we lack the resolution to see events that lasted for mere geological moments. Our own story proves this point. If humanity ended tomorrow, and a new intelligent species arose 50 million years from now, would they ever know we had existed? They might see faint chemical anomalies, traces of plastic molecules, or unusual carbon isotope ratios in thin sediment bands. But without extraordinary luck, they might never find a recognizable artifact. To them, Earth's history would look like one long procession of natural processes, with only a few mysterious blips hinting at something more. That is the core of the detection problem, and it leaves open the chilling possibility that we are not the first civilization to call this planet home. If ruins cannot survive deep time, and the thinness of the geological record makes civilizations nearly invisible, then the real trail we must follow lies in chemistry. Every industrial society alters its planet in ways that go beyond buildings, machines, or monuments. It transforms the very fabric of the environment, embedding signatures that cannot be produced by natural processes alone. Our own civilization is already leaving such fingerprints. They appear in plastics, in metals, in isotopic ratios, and in synthetic molecules that will persist long after our cities have dissolved into dust. This is why scientists investigating the Silurian hypothesis focus on chemical anomalies in sediments and rocks. These anomalies act like fossils of technology, lingering traces that could reveal whether Earth has hosted intelligence before. Plastic is one of the most striking examples. People often say plastic pollution will last forever, but that's not true on geological timescales. Plastics break down within thousands of years under heat, sunlight, and chemical attack. By the time the next ice age arrives, the bottles floating in today's oceans will be gone. Yet they won't vanish completely. Instead, plastics degrade into smaller fragments and release chemical compounds that infiltrate sediments. These compounds don't form naturally. They are artificial molecules born in factories and chemical plants. Once incorporated into rock layers, they become a permanent record, a kind of ghost molecule that whispers to the future. Something made me. Even when the original plastic is gone, the chemical fingerprint remains. What makes this signature powerful is its uniqueness. Nature follows strict rules in how it builds molecules. Industrial chemistry, however, forces atoms into arrangements that nature never uses. Flame retardants, stabilizers, and plasticizers are full of rare combinations of chlorine, bromine, or fluorine bound together in ways no volcanic process or biological pathway can produce. These molecules are like forged coins, stamped with unmistakable patterns of human technology. If discovered millions of years from now, they would tell an undeniable story. Intelligence was here. But plastics are only one example. The burning of fossil fuels changes the balance of carbon isotopes in the atmosphere, creating a signature that is recorded in tree rings, ice cores, and marine sediments. Normally, carbon cycles through the environment in balanced ratios. When coal, oil, or gas is burned, it injects carbon with lighter isotopic weights, shifting the natural pattern in ways that geologists can measure. This shift becomes locked into sediments as a permanent marker of industrial activity. Already, our emissions have created a chemical layer that will one day be visible in rocks. And if we can detect this now, then the same kind of anomalous shifts in ancient layers might represent the industrial activity of another species long gone. Other processes also leave telltale marks. Mining and metallurgy redistribute metals into patterns nature never creates. Copper, lead, zinc, and rare earth elements show distinctive isotopic ratios when processed by industry. Once these atoms are scattered into sediments, they remain detectable for millions of years. Nuclear activity is even more definitive. Splitting atoms creates isotopes that do not exist naturally on Earth. Some decay quickly, but others last millions of years, providing an unmistakable signal that a technological civilization once mastered atomic energy. If geologists in the distant future were to find these isotopes in ancient rocks, they would know beyond doubt that intelligence had been active at that time. In this way, chemistry becomes the archaeology of lost civilizations. Instead of searching for ruins, we search for anomalies in the language of atoms. Each molecule or isotope acts like a page in a hidden diary, recording the impact of technology on Earth. Already, scientists drilling deep into sediments have found layers with unusual chemical shifts, spikes in carbon, or traces of compounds that defy easy natural explanation. None of this proves an earlier civilization, but it shows us where to look and how to read the planet's memory. If another intelligent species rose and fell millions of years ago, its story might still be buried beneath us, not in statues or artifacts, but in the subtle fingerprints of chemistry that no amount of time can erase. One of the most powerful ways civilizations leave their mark is through the burning of fossil fuels, because this process changes the balance of carbon in the atmosphere in ways that are impossible to mistake once you know what to look for. Every source of carbon, whether it comes from living plants, volcanic eruptions, forest fires, or fossil fuels, carries a unique isotopic fingerprint. Carbon has several isotopes, most notably carbon-12 and carbon-13. Plants preferentially absorb lighter carbon-12, which means that fossil fuels, formed from ancient plants and organic matter, are unusually rich in carbon-12 compared to carbon-13. When we burn coal, oil, or natural gas, we release this lighter isotope into the atmosphere, and it shows up clearly in measurements of carbon ratios over time. Scientists track this shift today with alarming precision, watching as human activity steadily changes the isotopic balance of the entire planet. These changes don't just vanish, they become locked into ice cores, sediments, and rocks, where future scientists millions of years from now could still detect them. But here is where the story takes a strange and unsettling turn. Geologists studying ancient layers of rock have found rapid, dramatic shifts in carbon isotopes that do not match natural explanations. In several cases, the isotope ratios change so quickly that they suggest massive carbon releases over just a few thousand years. On a geological scale, that is like flipping a switch. Volcanic activity can release carbon, but its signature is different, heavier, and it usually happens over much longer spans of time. Forest fires can leave carbon signals too, but they tend to be scattered and irregular. What scientists have found in some sediment layers looks disturbingly similar to what we are doing right now, injecting huge amounts of light carbon into the atmosphere in a sudden burst. One of the most mysterious examples comes from the Paleocene-Eocene thermal maximum, about 56 million years ago. During this event, Earth's temperature rose by as much as 8 degrees Celsius in a geological blink. Oceans acidified, ecosystems collapsed, and many species vanished. The carbon isotopic record shows a rapid shift, the kind that looks almost identical to the industrial fingerprint we are leaving today. The cause is still debated. Some suggest massive volcanic eruptions or methane released from seafloor sediments. But the pattern raises an uncomfortable possibility. What if this was not natural at all? What if it was the result of a previous civilization burning through its own fossil fuels and destabilizing the climate, just as we are doing? The most puzzling detail is that in some cases, the carbon spikes are not smooth, but appear in pulses, as though the source was turned on and off. This is unlike volcanoes or natural methane releases, which tend to surge and then fade. The on-off pattern looks more like something controlled, something managed or mismanaged by intelligent hands. Imagine reading the rock record like a graph and seeing a sharp spike, then a pause, then another spike, each one representing a surge of carbon into the atmosphere. That is not the signature of a random natural disaster. It looks more like industry rising, falling, and then rising again. Adding to the mystery is what happens alongside these carbon spikes. The oceans, acting as giant carbon sponges, absorb massive amounts of carbon dioxide and become more acidic. We see this happening today, with coral reefs dissolving and marine food chains unraveling. In the ancient record, the same thing appears: sudden acidification, mass die-offs, and rapid environmental changes. To scientists, this pairing of isotopic carbon shifts with ocean chemistry changes looks eerily familiar. It is as though the Earth has already lived through an Anthropocene before ours, a time when a civilization altered the climate so dramatically that it left scars still visible tens of millions of years later. If that is true, then our planet holds a kind of mirror. We are not just altering the environment in unprecedented ways. We may be repeating a pattern that has happened before. And if previous civilizations did trigger such events, the outcome should serve as a warning. They vanished, leaving behind only chemical ghosts for us to puzzle over. The isotopic evidence suggests that intelligence and industry may not be enough to ensure survival. In fact, they may carry within them the seeds of destruction, visible in the rocks as sudden bursts of carbon that forever altered the course of life on Earth. The oceans are one of Earth's greatest record keepers, and at the same time they are among the most vulnerable systems to disruption. Today, we are witnessing firsthand how the release of carbon dioxide from burning fossil fuels is altering the chemistry of seawater. As carbon dioxide dissolves into the ocean, it forms carbonic acid, lowering the pH and making the water more acidic. Coral reefs are bleaching, shells of marine organisms are thinning, and entire food chains are beginning to collapse. This process, called ocean acidification, is happening at a speed that alarms scientists because it is faster than most natural systems can adapt. Yet, when geologists examine ancient sediments, they find chemical signatures showing that this has happened before. Oceans have rapidly acidified in the past, sometimes coinciding with mysterious mass extinctions. And what makes this especially unsettling is how similar those ancient events look to what we are experiencing now. Natural processes can acidify oceans, but they typically unfold over millions of years, allowing marine life time to adjust. Volcanic eruptions or asteroid impacts can cause more sudden disruptions, but they leave behind other obvious markers, such as iridium layers or vast basalt deposits. In contrast, some past acidification events show none of those natural fingerprints. Instead, the evidence looks strikingly industrial. The speed of change, the selective patterns of extinction, and the combination of chemical anomalies all mirror the impacts of modern human activity. It is as though the oceans have already endured an Anthropocene-like shock long before we arrived. One of the most intriguing aspects is the selectivity of these extinctions. When a natural disaster strikes, it tends to kill indiscriminately. An asteroid impact devastates ecosystems at random, wiping out entire lineages regardless of size or complexity. Volcanic winters can plunge the planet into darkness, starving both simple and complex organisms alike. But during certain acidification-driven events, the extinction pattern looks very different. Large, specialized animals disappear while smaller, more adaptable ones persist. Complex food webs collapse, while simple bacteria and opportunistic species survive. This selective pruning resembles exactly what is happening now under human influence. We are not wiping out all life at once. Instead, we are destabilizing ecosystems in ways that target the most vulnerable species: corals, amphibians, large mammals, migratory birds, while leaving generalist species and invasive organisms to thrive. That kind of extinction signature is not random. It suggests systematic environmental pressure, the kind that industry and civilization create. The fossil record backs this up with eerie precision. In several intervals of Earth's history, ocean sediments show abrupt drops in carbonate deposits. Normally, the shells of marine organisms made from calcium carbonate settle on the ocean floor, forming thick limestone layers. But during acidification events, these shells dissolve before they can accumulate, leaving behind barren zones in the sediment record. These barren layers tell the story of oceans, so corrosive that entire ecosystems of shell-building creatures were wiped out. Alongside these chemical gaps, scientists also detect spikes of unusual compounds and isotopic shifts that suggest massive carbon injections. When you put these pieces together, the picture looks disturbingly artificial. Sudden carbon surges, rapid acidification, selective extinctions, and chemical anomalies that persist for millions of years. The question, of course, is what caused them. Some researchers argue for methane releases from frozen hydrates beneath the seafloor, triggered by natural warming cycles. Others propose colossal volcanic eruptions that belched carbon dioxide into the atmosphere. But neither of these explanations fits perfectly. Methane releases don't tend to produce the pulsing on-off pattern of carbon spikes we sometimes see. Volcanism leaves behind unmistakable geological scars, and in some of these cases, such scars are missing. What remains is a mystery that looks increasingly like our own impact today. It raises the possibility that long before humans, another civilization may have burned through carbon-based fuels, changed the chemistry of the oceans, and triggered extinctions that reshaped life on Earth. If that is true, then ocean sediments become more than just a record of natural history. They are a warning etched into stone, telling us that civilizations may come and go, but the oceans remember. Every acidification leaves scars that last for millions of years, scars that future species can read like crime scene evidence. We are currently writing our own entry in this record, with reefs collapsing, seas acidifying, and extinction patterns forming that will be recognizable to anyone who digs through the sediments of the future. The oceans tell us that our crisis is not unprecedented. It may even be part of a repeating cycle, and if other civilizations fail to survive their own acidification events, then the question becomes chillingly clear: will we learn from the scars of the past, or will we join them as another vanished chapter in Earth's deep history? Metals are the hidden backbone of every technological society. Our phones, computers, power grids, vehicles, and even renewable energy systems all depend on precise combinations of copper, tin, zinc, lead, and the rare earth elements. These materials are dug from the earth in vast mining operations, concentrated, refined, and then scattered back into the environment in ways that nature itself would never arrange. Unlike stone or wood, which degrade without leaving much trace, metals carry with them isotopic and geochemical signatures that can persist in the rock record for millions of years. If a civilization before ours ever rose to industrial heights, one of the clearest places to look for its existence is in the patterns of metallic distribution left behind. Consider copper, one of the first metals humans ever worked with. In nature, copper is dispersed relatively evenly. Its deposits formed by predictable geological processes, such as hydrothermal activity and sedimentary layering. But when a civilization begins to mine and refine copper, the distribution changes. The richest ores are extracted first, leaving behind depleted zones and low-grade material. Archaeologists can detect this pattern from human history. Bronze Age miners targeted high-quality ores, and the isotopic fingerprints of their smelting show up in ice cores and sediments thousands of miles away. The same logic applies on a much larger scale. If an ancient industrial society extracted and dispersed metals, its activity might still be detectable in the way certain regions today appear mysteriously depleted compared to what geology predicts should be there. The rare earth elements make this story even more compelling. These 17 obscure elements, with names like neodymium, dysprosium, and terbium, are essential to modern electronics and renewable energy technologies. They are also extremely scarce, concentrated only in a handful of deposits worldwide. Humanity is rapidly consuming these elements, spreading them into countless devices and products where they become too diluted to recover. Once dispersed, they cannot easily be reconcentrated without advanced recycling technologies. This creates what scientists call a resource bottleneck. Once a civilization depletes its easily accessible reserves, future civilizations will struggle to climb the same technological ladder. Geological studies have found sediment layers millions of years old, with depletion patterns that resemble over-extraction of rare earths. These anomalies suggest that someone, long before humans, may have harvested these critical resources, leaving behind a planet with scarcer supplies for the next rise of intelligence. Then there are isotopic fingerprints, the subtle atomic differences that result from refining and smelting. Every time we process a metal, lighter isotopes behave slightly differently than heavier ones, leaving behind distinctive ratios. Lead is a prime example. Ancient smelting shifted lead isotopes in ways that are measurable even today. Scientists drilling in Greenland ice cores can detect the pollution left by Roman lead mining 2,000 years ago. If such signatures remain detectable from small-scale ancient industry, then the work of a full-fledged industrial civilization millions of years ago would have left even deeper and more widespread isotopic scars. Some sediment cores already show anomalies in metal isotopes that lack convincing natural explanations, raising the possibility that they are remnants of technological processes now forgotten. The pattern is like an orchard, where someone has picked the ripest fruit long before you arrived. Geologists expect certain distributions of copper, tin, zinc, and rare earths, but in places they find that the richest deposits are mysteriously absent. Instead, the remaining ores are thin, scattered, and of lower quality. Natural processes can explain some irregularities, but others look oddly systematic, as if some unknown miners had already harvested the best materials and left the rest behind. When these depletion zones line up with isotopic anomalies and strange chemical patterns, the evidence begins to resemble not random geology, but the aftermath of deliberate exploitation. What makes this so important is that metals, unlike buildings, cannot simply vanish without a trace. Even when scattered, their fingerprints linger in sediments and isotopes. A vanished civilization may not have left us its machines, but if it smelted copper, forged alloys, or mined rare earths, the chemical consequences of those actions could still be read in the Earth's crust. And when scientists find unusual gaps in expected mineral deposits or isotopic ratios that don't align with volcanic or sedimentary processes, they must consider the provocative possibility that those marks are the industrial shadows of a civilization long gone. If this is true, then our own time is not unique. We are merely the latest miners in a cycle of civilizations, each one digging deeper into the finite resources of the planet, each one leaving chemical scars that speak across the abyss of geological time. Nuclear technology may be humanity's most unmistakable fingerprint, because unlike plastics or carbon isotopes, its traces are truly unique. Natural processes can mimic some forms of pollution, but there are no volcanoes or biological pathways that create certain radioactive isotopes. When we split atoms in reactors or weapons, we leave behind isotopic combinations that could never occur without technological intervention. These isotopes are, in a sense, atomic graffiti etched into the very fabric of matter, and they persist long after the civilization that made them disappears. Even if every nuclear power plant, warhead, and laboratory vanished tomorrow, the isotopic ghosts of our nuclear age would remain detectable in rocks, ice, and sediments for millions of years. For scientists asking whether earlier civilizations might have existed, these nuclear fingerprints are among the most definitive signs they could hope to find. Consider plutonium-244, an isotope not found naturally on Earth. It has a half-life of 80 million years, meaning that even tens of millions of years from now, traces of it will still exist wherever it was created and dispersed. Uranium enrichment, another hallmark of nuclear activity, produces specific ratios of uranium isotopes that are different from those found in nature. These altered ratios are locked into materials and sediments, like atomic barcodes that can be read by geochemists long after the facilities that produced them are gone. Already, nuclear weapons testing in the mid-20th century has created a distinct global fallout signature. Artificial isotopes such as cesium-37, strontium-90, and iodine-129 are now embedded in tree rings, ice cores, and deep-sea sediments around the world. Future scientists studying these layers would find a sharp line in Earth's chemical diary, a radioactive horizon that would mark our time as clearly as the iridium layer marks the asteroid impact that ended the dinosaurs. What makes nuclear signatures especially compelling is their resistance to erasure. Buildings collapse, artifacts corrode, plastics degrade, but isotopes follow mathematical decay laws that allow their origins to be reconstructed even after millions of years. Think of them as radioactive breadcrumbs scattered through geological time. Scientists could find an anomaly in a sediment core, measure the isotope ratios, and trace them back to their artificial origins, even if all evidence of reactors or warheads had long since disappeared. Some sediment layers already contain unexplained isotopic anomalies. These do not match volcanic activity or cosmic rays, the usual natural sources of rare isotopes. Instead, they hint at processes more controlled and precise, processes that sound suspiciously like nuclear technology. The chilling implication is that if another civilization discovered atomic power millions of years before us, we might still be able to find traces of it today in the form of these unnatural isotopes. Even if they vanished without a single artifact remaining, their nuclear age would be written into the rocks. And this possibility opens another line of thought. Perhaps we have already seen such anomalies, but dismissed them as errors or unexplained curiosities. After all, scientists are trained to seek natural explanations first. If we stumbled upon an ancient plutonium deposit today, how many researchers would dare to suggest it was evidence of a long-lost civilization rather than an unusual natural occurrence? Beyond nuclear signatures, synthetic molecules also tell a similar story. Industrial chemistry can create compounds that nature never assembles on its own. Complex polymers, halogenated hydrocarbons, and other nothing molecules can break down, but their fragments can persist in sediments for millions of years. These fragments act like chemical fossils, offering clues that advanced chemistry once existed. Already, scientists have found unexpected compounds in ancient layers, molecules that look suspiciously artificial. They may not prove a vanished civilization, but they demonstrate the kind of markers one should be looking for if such a civilization did exist. Taken together, these nuclear and synthetic fingerprints represent perhaps the most unambiguous evidence of intelligence. A pyramid can erode, a city can vanish, a machine can rust away, but a plutonium atom will remain as undeniable proof of technology. If we ever discover such isotopes in deep ancient sediments, the conclusion would be inescapable: we were not the first. And the irony is that our own nuclear age guarantees that if another intelligence arises millions of years from now, they will be able to say the same thing about us. Our legacy may not be the monuments we built or the culture we created, but the radioactive signatures we left behind, glowing faintly in the rocks of the far future. Long before humans, Earth experienced what could be described as its first pollution crisis: the Great Oxidation Event. About 2.5 billion years ago, tiny cyanobacteria evolved the ability to perform photosynthesis, releasing oxygen as a byproduct. At the time, oxygen was not a life-giving gas, but a deadly poison. Most organisms on Earth had evolved in a low-oxygen environment and could not tolerate the new atmosphere. As oxygen levels rose, it triggered a mass die-off, suffocating countless species and altering the chemistry of the planet forever. Iron dissolved in the oceans, rusted out, forming vast deposits of banded ironstone that we still mine today. Sulfur cycles shifted, and entire ecosystems collapsed. From our perspective, oxygen feels natural and essential, but billions of years ago, it was a contaminant, a toxic pollutant that reshaped life. This event proves a key point: global chemical change does not require advanced technology. Even simple life forms can transform a planet. This is important because it demonstrates how enduring chemical fingerprints can be. The Great Oxidation Event left behind unmistakable isotopic signatures that persist billions of years later, written into the rocks like a permanent diary. If bacteria can leave behind such evidence of their impact, then surely an intelligent, industrial civilization would leave even stronger signals. The oxidation event shows that Earth records massive environmental disruptions, and it suggests that similar records might already exist for civilizations that came and went long before us. One of the most puzzling signs comes from what geologists call ancient dead zones in the oceans. These appear in sediment cores as dark, barren bands where no fossils, shells, or organic material exist. They represent times when the oceans became so toxic and oxygen-starved that virtually no life could survive. Natural processes can cause smaller dead zones, such as when rivers dump excess nutrients into coastal waters, creating algae blooms that choke off oxygen. But some of the ancient dead zones are far larger and more severe than anything natural processes alone can explain. They stretch across entire ocean basins, lasting thousands of years, and their chemical profiles show extreme pollution that looks less like volcanism and more like industrial contamination. What makes these dead zones even more suspicious is their location. They often cluster around continental margins and ancient river systems, exactly where human industry concentrates today. These are the same regions where factories dump waste, where cities release sewage, and where industrial chemicals wash into the sea. The chemical analysis of these sediments shows elevated levels of heavy metals and synthetic-like compounds, combinations that nature rarely produces without help. To some researchers, these signatures resemble a crime scene, evidence of massive environmental poisoning without a natural culprit. Now imagine this scenario. A technological species, millions of years ago, used industrial processes that, just like ours, overwhelmed the oceans with waste. Over time, their pollutants spread across seas, killing ecosystems and leaving behind vast lifeless zones. When their civilization collapsed, the dead zones slowly healed, but the sediments retained the memory of that destruction. Today, when we drill into those layers, we see the scars, but not the hand that caused them. From a scientific perspective, it is tempting to explain everything with volcanism or other natural disasters. But some anomalies do not fit neatly into those categories, and their eerie resemblance to modern pollution should not be ignored. The Great Oxidation Event and these mysterious ancient dead zones together suggest that Earth is sensitive to the activities of both microbes and civilizations. Just as cyanobacteria reshaped the planet by accident, a technological society could reshape it by design or by negligence. Both leave long-lasting chemical signatures, but only one has the capacity to consciously alter planetary systems. The paradox is that the stronger the civilization, the faster it may drive itself into collapse, leaving behind only chemical ghosts. If this cycle has happened before, then we may simply be the latest chapter in a repeating story, one in which the oceans themselves serve as both witness and judge, recording in their depths the rise and fall of civilizations that thought they were eternal. Copper should be one of the most predictable elements in Earth's crust, distributed by volcanic flows, hydrothermal vents, and sedimentary layering in ways that geologists can model with remarkable accuracy. Yet when large-scale surveys map out the global distribution of copper, tin, and zinc, the results often don't quite match the predictions. In some regions, the richest deposits are mysteriously missing, while others show unusual clustering that doesn't line up with natural geological processes. This strangeness is most apparent in the very metals that are most useful for technology. Copper and tin combine to form bronze, which for humans marked the dawn of an entire age. Zinc is essential for alloys like brass and for galvanization. When these metals appear together in concentrated, convenient deposits, they almost seem too useful to be accidental. And when those deposits appear oddly depleted, the suspicion arises that someone might have gotten there first. Archaeologists already see this pattern on smaller timescales. Ancient mines from human history show clear evidence of selective extraction. Bronze Age miners targeted the richest ores, leaving behind lower-grade materials that still bear the scars of their chisels and fires. In the Andes, in Africa, in the Middle East, archaeologists have uncovered evidence that people systematically removed the highest quality ores thousands of years ago. These activities left measurable geochemical signatures. The remaining rocks are not just emptier, they also carry isotopic ratios altered by smelting. If such effects are visible after only a few millennia, imagine what might be detectable from industrial-scale mining conducted millions of years ago. What makes this especially compelling is that some depletion patterns are far older than any known human activity. Geological surveys reveal rock formations that show systematic extraction-like features dating back tens of millions of years. While mainstream science attributes these irregularities to unusual natural processes, they bear uncanny resemblance to the kind of depletion left by miners exploiting concentrated deposits. The problem is that it is hard to distinguish between natural anomalies and the fingerprints of civilization when the evidence is buried so far in the past. If miners had walked the earth long before us, they would have left behind a landscape that looks strangely familiar yet officially unexplained. This leads to what researchers sometimes call the orchard problem. Imagine walking into a fruit orchard that has been picked over by an earlier visitor. The ripest fruit from the lowest branches is gone, and only scattered, smaller pieces remain higher up or hidden in corners. You would know someone had been there by the pattern of what was missing, not by finding the person themselves. Earth's crust may show the same signs. The best ores harvested long ago, leaving us to wonder why some deposits are poorer or oddly arranged compared to natural expectations. The strange alignment of depletion with technological usefulness, the very metals most critical for building tools, machines, and energy systems, only deepens the suspicion. To complicate things further, isotopic anomalies in certain metal deposits raise even more questions. When humans refine metals, the lighter isotopes behave slightly differently than the heavier ones, creating ratios that don't occur in untouched ores. Scientists have already measured these shifts in ice cores and sediments, resulting from relatively small-scale human activity. If a previous civilization smelted metals on a large scale, similar isotope ratios should be preserved in the rock record, and in fact, some anomalous isotopic signatures have been detected in ancient layers without a convincing volcanic or sedimentary explanation. They are simply there, odd fingerprints in the crust that suggest someone was separating and processing metals long before us. The implications are profound. If earlier civilizations exploited Earth's mineral wealth, they may have faced the same challenges we do now. Depletion of finite resources and the difficulty of sustaining growth once the richest deposits are gone. This raises the possibility that Earth itself has a kind of memory, recorded not just in fossils or sediments, but in the absences and distortions of its mineral distribution. Each round of intelligence that rises might strip away the best resources, leaving the next one with thinner margins and steeper technological hurdles. We may not be the first to build a world on copper and tin, and if so, our mining is just another verse in an old repeating song. The rocks remember even when history does not. Even the most imposing monuments of human civilization are fragile when measured against the vastness of geological time. We like to think of the Great Pyramid of Giza, the Colosseum, or Mount Rushmore as timeless, but science shows otherwise. Stone erodes, metal corrodes, foundations crack. The processes are relentless, grinding away at human achievement with every freeze-thaw cycle, every gust of wind, every drop of acidic rain. Studies suggest that Mount Rushmore, carved into granite and seemingly permanent, will become unreadable within 500,000 years. The Great Wall of China will be untraceable within 2 million years. Even the Great Pyramid, which has endured for more than 4,000 years, is vanishing grain by grain and may be reduced to little more than a mound of rubble within tens of thousands of years. Multiply that by millions, and it becomes clear that even the most durable human structures will vanish completely. The planet itself is a patient eraser. This leads to what scientists call the monument paradox. If earlier civilizations built monumental structures like ours, why don't we find their ruins? The answer lies in the mathematics of erosion. Geological forces do not care about human ambition. Rainwater seeps into cracks, freezes, and expands, splitting stone. Heat expands minerals at different rates, causing structures to fracture. Wind blasts particles against exposed surfaces, carving them down grain by grain. Even the hardest granite yields to these processes given enough time. Add earthquakes, volcanic activity, rising seas, and glaciers grinding across continents, and any monument, no matter how massive, is doomed. The deeper question is whether something might remain, some material so durable or so alien to natural processes that it could endure far beyond normal decay. Modern technology produces such materials: synthetic diamonds, engineered ceramics, and certain crystalline structures could, under the right conditions, persist for hundreds of millions of years. In fact, geologists occasionally find unusual formations that defy easy classification, structures that may simply be the products of strange geology, but which some speculate could be the heavily weathered remnants of artificial creations. The challenge is that erosion makes even the most engineered objects blend into the background of natural rock. A monument buried under layers of sediment might last longer, but then it becomes indistinguishable from surrounding stone unless it contains materials that nature never produces on its own. That is where synthetic molecules come in. Industrial chemistry leaves behind compounds no volcanic vent, ocean current, or biological process could create. These synthetic molecules act like chemical fossils, subtle but undeniable. Even when the original artifacts have long since vanished, the breakdown products of these materials linger in sediments. With modern techniques, scientists can detect them at concentrations as low as parts per trillion. In some cases, unusual molecules have been found in ancient rock layers, their origins unexplained but suspiciously artificial in structure. Unlike eroded stone or corroded metal, these molecular traces cannot be disguised as natural. They are chemical signatures of technology, markers of a civilization that once altered the planet in ways geology alone could not. This reality reshapes how we think about permanence. Our monuments may crumble, our machines may rust, and our cities may vanish beneath forests or deserts, but our chemistry is harder to erase. Future scientists may not find the skeleton of New York or the ruins of Shanghai, but they will find plastic-derived molecules, isotopic anomalies, and synthetic compounds that nature could never have arranged. And if we were to find the same kinds of anomalies in ancient layers, chemistry too advanced to be explained by nature, then we would be forced to ask the most unsettling question of all: who put them there? Perhaps civilizations before us never built pyramids or statues meant to last. Perhaps their true legacy, like ours, is chemical rather than architectural. And that legacy, once written into the rocks, may be the only monument that time cannot erase. Genetic engineering is often described as humanity's most audacious step, the moment when life itself becomes a canvas for design rather than a product of chance. In just a few decades, we have gone from sequencing DNA to rewriting it, splicing genes from one organism into another, editing precise sequences with CRISPR, and even designing entirely new genetic codes. These interventions leave behind traces, markers in DNA that natural evolution does not produce. Inserted genes often carry artificial regulatory elements, repeated sequences or vector signatures from laboratory tools. These modifications are detectable long after the organism itself has perished, because they remain embedded in the genetic record. Already, scientists can identify engineered changes in modern crops, livestock, and microbes. But what happens when we turn our eyes backward in time to the genomes of extinct species? What if we discover markers that suggest something tampered with them long before humans existed? Paleogenetics, the study of ancient DNA, has unearthed surprising patterns that hint at precisely this possibility. Some extinct organisms show abrupt leaps in adaptation that appear too coordinated to be explained by slow Darwinian processes. Traits that should have taken millions of years to develop instead appear in the fossil record within a few thousand, or even less. For example, entire metabolic pathways seem to emerge suddenly, granting an organism the ability to process new food sources or resist diseases without a gradual buildup of intermediate steps. This kind of genetic punctuation looks remarkably similar to what modern geneticists do when they insert new genes directly, rather than waiting for natural selection to stumble upon them. It raises the question: are we looking at the fingerprints of nature's rare bursts of accelerated change, or at evidence of a civilization tinkering with genomes long before us? Think of genetic engineering like editing a book. Natural evolution is like an endless series of typos, most of which make the story worse. Over immense spans of time, a few lucky accidents improve the text, and selection preserves them. But engineering is different. It is like a skilled editor suddenly inserting entire paragraphs, fixing grammar, or restructuring a chapter. The difference is obvious if you know how to read the manuscript carefully. In DNA, the difference comes down to patterns of insertion, repetition, and organization. Artificial edits leave telltale signs, cut sites, duplicated sequences, and coding elements borrowed from unrelated species. And astonishingly, some ancient DNA fragments display such signatures, with genetic structures that look statistically improbable as products of chance alone. The most unsettling examples involve extinct species that underwent bursts of change across multiple traits at once. Instead of adapting step by step, they appear to leap into new forms with improved disease resistance, faster metabolism, and more efficient reproduction, all within a short geological window. That kind of sudden multi-trait optimization is nearly impossible through natural selection, but it is exactly what modern genetic engineering aims to accomplish. When researchers see these patterns, they often struggle to explain them. Are they flukes of incomplete fossil sampling? Are they artifacts of degraded DNA? Or are they hints that something or someone was guiding evolution in deep time? If true, this possibility reframes the entire story of life on Earth. It suggests that intelligence and technology may not only rise and fall, but may also intervene directly in the evolutionary process, leaving behind modified species as living fossils of their existence. Even if their cities, machines, and monuments vanished without a trace, their edits to DNA could persist across generations, echoing forward into the present. Some species alive today could carry within their genomes fragments of engineered code, ancient modifications that have long since lost their original context. We may be unknowingly walking among the living remnants of a civilization that sculpted life millions of years ago. The deeper implication is that Earth itself may be a kind of genetic palimpsest, rewritten again and again by different hands across deep time. Each wave of intelligence may have left behind organisms subtly or radically altered, while their own societies vanished into dust. In that sense, the fossil record is not just about bones and shells. It may also be about edits to the genetic software of life. And if we in our time are now making the same choices, then we must ask the haunting question, are we the first to wield this power, or simply the latest to rediscover a tool that others once used before their world collapsed? Earth's history is divided into chapters known as geological ages, each one marked by sharp transitions recorded in rock layers. These transitions are dramatic, often involving sudden climate shifts, widespread extinctions, or chemical anomalies in sediments. Most are linked to well-known natural causes, massive volcanic eruptions, asteroid impacts, or the slow march of plate tectonics. But not all of them are so easily explained. Some boundaries in the geological record look eerily similar to what scientists now call the Anthropocene, the human-driven age of environmental transformation. They show rapid warming, abrupt acidification of oceans, selective extinction of species, and strange chemical fingerprints that suggest something more than nature was at work. If these signs were not tied to human activity today, they might hint at technological civilizations that came and went long before us. One of the most compelling examples is the Paleocene-Eocene thermal maximum, PM, about 56 million years ago. During this event, global temperatures soared by as much as 8 degrees Celsius in just a few thousand years. The ocean's acidified ecosystems collapsed and many species vanished, while others migrated in desperate attempts to survive. The carbon isotopes recorded in rocks and sediments from this period show a massive injection of light carbon into the atmosphere, the same fingerprint produced today by burning fossil fuels. Scientists debate the cause. Some argue that volcanic activity released vast stores of carbon dioxide. Others propose that methane hydrates buried under the seafloor destabilized, releasing greenhouse gases in bursts. But the exact pattern of isotopic shifts, sudden, pulsed, and overwhelming, bears uncanny resemblance to industrial emissions. If humanity were to vanish tomorrow, future geologists would see a nearly identical signature when studying our time. What makes these proto-Anthropocene events even stranger is their periodicity. Geological records suggest that such rapid transitions occur roughly every 50 to 100 million years. The timing is suspiciously regular, as if intelligence and technology repeatedly rise, alter the environment dramatically, and then collapse, leaving only a chemical scar in the rocks. Earth may not host a singular, unprecedented civilization. It may instead recycle civilizations, one after another, each separated by tens of millions of years. Each wave climbs the ladder of intelligence, burns through resources, changes the climate, and then disappears, leaving the stage empty until evolution starts again. The selectivity of extinctions in these intervals strengthens the suspicion. Natural disasters tend to kill indiscriminately, wiping out entire ecosystems regardless of complexity. But some of these extinction events display targeted patterns. Large animals vanish while smaller ones survive. Specialized organisms collapse while generalists persist. This selective pruning looks more like the stress of industrial disruption than the randomness of an asteroid or volcano. It is disturbingly similar to the extinction patterns unfolding today under human influence, where complex food webs are unraveling while opportunistic species thrive. The recurring nature of these signatures suggests something deeper. Perhaps intelligence is not a rare fluke, but an inevitable evolutionary outcome. Nervous systems grow more complex, problem-solving abilities expand, social cooperation deepens, and eventually some species begins to shape its environment on a planetary scale. From there, the trajectory may be predictable: rapid industrialization, global chemical disruption, resource depletion, collapse. If so, Earth's geological record is not merely the story of life, but the repeating rhythm of civilizations that rise and fall, each one etched briefly but indelibly into the strata. For us, the unsettling question is whether we are nearing the same fate. If we are part of a cycle, then the thin layer of synthetic chemicals, plastic-derived molecules, isotopic shifts, and radioactive isotopes we leave behind will be just one more proto-Anthropocene horizon for some future species to puzzle over. They may find our signatures the way we find the PTM, strange, unexplained, and hauntingly familiar. And like us, they may wonder whether they are truly the first or simply the latest. The search for evidence of past civilizations, hidden within Earth's deep history, forces us to confront questions that are both scientific and philosophical, both unsettling and inspiring. When we look at the planet's geological record, we see not a clean and orderly book, but one written in fragments, pages torn, entire chapters compressed into layers thinner than paper. Within those layers are signatures, chemical shifts, isotopic anomalies, synthetic molecules, and unexplained extinctions that whisper of possibilities we are only beginning to imagine. The Silurian hypothesis, the idea that industrial civilizations may have risen and fallen long before humanity, is not a claim of certainty, but a lens through which to view the mysteries of Earth with fresh eyes. It compels us to ask whether we are truly unique, or just another verse in a song the planet has been singing for hundreds of millions of years. What makes this hypothesis so haunting is the fragility of civilization itself. We live surrounded by monuments, skyscrapers, highways, and machines, convinced of their permanence, yet science shows they will crumble into dust within a blink of geological time. Even our most durable creations, from pyramids to satellites, are temporary compared to the slow churn of tectonics, erosion, and chemical weathering. Within a few million years, nearly every physical trace of our existence will be gone, leaving behind only the most subtle imprints: depleted mineral deposits, disturbed isotopic ratios, the faint chemical ghosts of plastics, and the radioactive echoes of nuclear technology. If we are honest, this is all that future species would have of us, and if we acknowledge that, then we must also admit that if other civilizations once walked this earth, they too would have been reduced to little more than chemical shadows. Throughout Earth's history, we see patterns that mirror our own impact: sudden bursts of carbon into the atmosphere, rapid warming, ocean acidification, selective extinctions, and strange anomalies in metal and mineral distribution. Some can be explained by volcanism, asteroid impacts, or natural cycles, but others are harder to reconcile, bearing an unsettling resemblance to the environmental consequences of industrial activity. The Great Oxidation Event reminds us that even microbes can change the chemistry of the entire planet. If bacteria could leave such lasting scars, how much deeper would the scars of a technological society run? Perhaps some of the mysteries we attribute to natural catastrophe are in fact the echoes of civilizations that destroyed themselves, their rise and fall recorded only in chemistry rather than stone. Yet the Silurian hypothesis is not just about the past, it is a mirror held up to the present. It reminds us how precarious our own position is. We are burning through finite fossil fuels, exhausting rare earth elements, destabilizing ecosystems, and altering the climate faster than nature can adapt. If civilizations before us faced the same pressures and collapsed, then our path is not unique, but cyclical. We may be repeating the same mistakes written into the deep record of the Earth, blind to the lessons etched in layers of rock. The silence of past civilizations may not be proof they never existed, but a warning of what happens when technological ambition outruns ecological wisdom. And so the ultimate question is not whether others came before us, but whether we will leave behind more than just chemical scars. Will future species, millions of years from now, look back at our thin sedimentary layer and see only another failed experiment in intelligence? Or will they find evidence that, unlike the ones before us, we learned to live within planetary limits, to sustain a civilization not for millennia, but for millions of years? The choice remains ours, but the clock is ticking. The rocks have seen it all before: extinctions, recoveries, and perhaps civilizations rising and falling like waves upon the shore. Our legacy is being written now, not in stone monuments or glass towers, but in the chemistry of the Earth itself. What story will we leave for the future to find?